Ah!
Hello!
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 Ta-da!
All right, welcome to the Moon
And back!
and back
And back!
and back.
And back again!
Excellent. Today we are going to be talking about some fabulous planets, but before that, my name is Will, and this is my assistant.
Sean!
Excellent! And last week we were talking about gas giants. Very, very gassy giants. We talked about the good old ones, Jupiter and the one with that ring, just engaged, Saturn. But we also know that two other planets in our system are also gas giants. But last week we told you maybe they're not! And that's because, as of recently, they have been reclassified as good old things known as ice giants. Ice giants. And those are our good old friend, Uranus. There we go. Good old friend, Uranus. Now, let's go ahead and get into Uranus. But now, keep in mind that once again, you'll be having to draw out, color, design your own probe, much like you have the last 2 weeks, on which one you want to explore and examine and how you'll do that. So, we are going to go ahead and get into Uranus, but keep that in mind.
So to start off with, guys, what makes an ice giant is the fact that its core is rocky and icy, and it has an almost solid core where the gas giants didn't at all. So that's kind of the differentiator and why we now have Uranus as a ice giant. So a little bit of stats about Uranus. Its orbit is 84.02 years. So that's like 84 years and 2 months maybe. Our distance from the sun, remember guys, an AU is the distance between the sun and the Earth. So the distance for Uranus at its closest is 18.33 AUs, and at its farthest, it is 20.11 AUs away. So it's really far away, so it doesn't get a lot of sunlight. So what do you think that has to do, and why it makes it an ice giant versus why it makes it a gas giant? Next, we have our known satellites, and it has 27, but a lot of these weren't discovered until very recently. Its mass is 14.53 Earths, so it's almost 14.5 times the size of Earth, which is really big, but it wasn't as crazy huge as, say, Jupiter was. Its gravity, however, is kind of low. It's only 0.88 of 1 Earth's gravity, and we're going to find out why that's so crazy later, and why something so huge can have such a small surface gravity. Its atmosphere is 83% hydrogen, 15% helium, and there is some ice in there as well. There's methane ice, there is water ice, and there's also ammonia ice as well. And then finally, we can only find the average temperature of Uranus, and that is negative 388 degrees Fahrenheit on average, so it's quite cold there. So if you're going there, make sure you bundle up nice and warm.
Bundle up, nice and warm. Now, we're going to go ahead and start off with Uranus and how it was discovered. There was a man in 1781 named William Herschel, and he decided he was going to go ahead and start looking at some of the more dim stars in the sky. If you ever look in the sky, you'll see that there are some mostly very bright ones and some ones that are a lot dimmer, and so he decided he would look at those dim ones, and so he started looking at them, and he noticed that one of them looked a little bit different. And what I think he probably was noticing, his main difference, is if you ever look in the sky and you're looking at a star and its light kind of does a flicker, or twinkle twinkle little star, if it's twinkling, that means it's a star. But if that light is standing still and not twinkling, it is probably because you are looking at a planet. And so planets are not giving off their own light, they're reflecting it from the sun. So there's no energy difference. They're just reflecting, which means they give off a single light without any twinkling. And so that was how we discovered Uranus back in 1781. Now, it also has rings. They're not as big as Saturn's, but they are still there. And when we discovered rings on Uranus, it actually gave us a little bit of an indication that rings are a thing that are kind of common in planets. The difference is Saturn just has some very, very big rings that are very large and very visible to see. As where Uranus's and Jupiter's and the other planets' rings are a little bit more difficult to see. Like we were talking about, it most likely has a very large rocky core with some ice in there, which means that it's an ice giant. A very, very fun fact that the girls may want to know and the boys may also want to know is that because there's so much pressure here, it is suspected that on that rocky core there is probably 1 trillion diamonds down there. So girls, you're going to want to know so you can get your diamond, and boys, that's where you're going to have to travel to get a diamond for that girl. Anyways, so there's diamonds there. Now, the next fun point is its atmosphere. It has a lot of methane in it. Now, obviously, it's predominantly hydrogen and helium, but it also has a lot of methane in it. And because it has methane in it, methane takes red light and it absorbs red light. It absorbs it. So we're not going to see any red in the atmosphere. So when we look at it, we're not seeing that. What we're going to see instead is the fact that methane scatters blue-greenish light, which gives Uranus that nice bluish-green coloring. And so, if my assistant behind that camera can hand me Uranus, that blue-green one. Here we go. We have Uranus, our nice blue-greenish planet right here, due to its methane. Now, we're going to talk about why we could only find an average temperature, and we couldn't find a nighttime and a daytime temperature. And that has to do something with axial tilt. What is it called?
Axial tilt.
And now before we get on to explaining the axial tilt of good old Uranus here, we are going to first have to talk about what is axial tilt. And to do that, I'm going to need the Earth. Excellent. So I now have the good old Earth. And we all know that the Earth spins, much like this. Woo! It spins. However, in relation to the sun, which is right over here, now it's not this close to the sun, and the sun is much bigger than that. So let's keep that in mind. The sun is much, much bigger. If we had the sun in here compared to this size Earth, it would fill up the entire frame of the camera, and you wouldn't be able to see where the sun started or ended. So keep in mind the sun is much bigger than that, and the Earth, if it was basically. So we're gonna use this big one so we can at least see. Now we all know that the Earth spins like this. Now that is something that we know because we have daytime and nighttime, which means if we are right over here in California, in Southern California, when we're facing away from the sun, we have nighttime. But when we turn, we have daytime. And then it keeps rotating. That's how we get our beautiful sunsets and sunrises. But there is another interesting thing. We have seasons. Now, our seasons are caused by that thing called axial tilt. And what that means is that our axis, basically if you imagine there's a pole from the top of the planet all the way to the bottom, is tilted. Something like this. Just a little bit. So that as we're rotating around like this, we're still getting our daylight and our nighttime, all right? But if we're gonna move that sun right here in the middle, we are also not only just revolving like this, we're also orbiting the sun, which means if we're here in California during daytime, as we go around 360 days, about when we get to that other side, we are going to be still getting nice in daytime as we rotate, but technically in some ways we're closer to the sun on one side. And so as we go around like this on that sun, because of the axial tilt, we have nice good old summer, fall, winter, and spring because of how that axial tilt is.
Also, because of that axial tilt, we have certain seasons different in the northern hemisphere than we do in the southern hemisphere.
Mm-hmm.
So, during summertime in the northern hemisphere, it's winter time in the southern hemisphere and vice versa. So, in Australia, when we're celebrating Christmas, they have days that are over 110 degrees. That doesn't sound like a very white winter to me.
No, it doesn't. But it's because of that axial tilt, because during the winter, because of the tilt, they're closer to the sun by just that much on that tilt. So right now you can see America is farther away from the sun than, say, Australia is. And just that much different is going to change the temperature just that much. However, when we go all the way to the other side, America is now closer to the sun than Australia, as Australia is down over here. It's tilted away. So it is experiencing winter when we're experiencing summertime. And that's because of axial tilt. It gives us our days and nights, but it also gives us our seasons. Now, I'm going to throw the Earth back at you guys. Woo! And I'm going to go ahead and grab Uranus back. Whoa! Uranus is a crazy one. Now, my Uranus is even smaller than the Earth, and that's not to scale. Uranus is much, much bigger. Remember, we talked about it. It's 14 times bigger. Still not bigger than the Sun. But I have labeled the axes of Uranus right here with some marker. So you can see this is, for instance, the North Pole of it, and this is, for instance, the South Pole of it. However, if this is the North Pole and this is the South Pole of Uranus, where my fingers are, this would be basically how the Earth is pointed. However, Uranus is not like that at all. It's pointed like this! Very much like this. It's not perfectly horizontal straight with it. It's got some degrees to it. But that means that the Uranus is rotating around and around like this, which means it's not getting daytime and suntime, or nighttime and daytime. It's basically just on one side getting nothing but sunlight. And then as it goes around, the other side is going to get nothing but daytime, and the other side is going to get nothing but night, which means that its temperature is going to be an average between one side and the other. And so we can't give you a nighttime and a daytime. But that axial tilt causes the planet to have some crazy seasons. Basically, I would think that it kind of has its own seasons, but its winter and its summer are going to be incredibly significantly different. Its winter is going to be much, much colder on one side in degree, and much, much, much hotter on one side degree. So because it has an atmosphere that's made up of hydrogen and helium and methane, as that changes as it goes around, it is going to have some crazy weather patterns that change and develop, just like we have seasons, but they're going to be even more drastic. So, that is our good old planet, Uranus. So, we're going to go ahead and throw Uranus and the sun right back at you. And we are going to go ahead and move on to our next one. Try not to whop me in the head with that one. All right. Our next one is the good old sea god Neptune. Neptune. He is also an ice giant, and his name is Neptune. It's a planet, of course. Remember we were talking about all the planets ended up getting Roman god names. And this one is Neptune, and he is very, very, very blue, which makes sense because they associated Neptune with their god, Neptune, who was the god of the oceans. Same guy as Poseidon, but they changed it from the Greeks. Anyways, let's go ahead and move it on over. He has an orbit of 164.8 days. Oh no, not days, years. It takes 168 years for Neptune to go all the way around the sun. That means he hasn't even made it around a whole time since I've been born, or even you've been born. Alright, let's go ahead and talk about distance from the sun. It's 29.81 AU at its closest, and at its farthest, it's 30.33 AU. Remember, AU is astronomical unit. That is the average distance from the Earth to the sun. Moving on, satellites. It has 14 known satellites. So that's not as many as some of the other gas giants, but it does have more than us, ourselves, Earth. Moving on, its mass is 17.14 Earths. 17.14 Earths. So it is more massive than Uranus. And its gravity is 1.14. So it's more than Uranus and more than Earth. Excellent. Moving on. Atmosphere. Atmosphere is 80% hydrogen, 19% helium. Its temperature in the daytime is 396 Fahrenheit, and at night it has 424 degrees Fahrenheit. Now, before we move on, what do those temperatures tell us? That we have a nighttime and a daytime. What does that tell us? That tells us something about its axial tilt. It has an axial tilt that is not super crazy wonky. It has something that is at least a little bit more up and down so that we're getting our daytime and our night times from it. Okay? Now,
there are some really cool things about Neptune, and the first one is the fact that when we discovered Uranus, a mathematician said, if there's a planet out there, there must be one farther. So they created a theorem that let them predict where Neptune would be. And that was a full 50 years before we actually first saw Neptune by a telescope. So we first discovered it on September 23rd, 1846, but it was in the late 1700s that people theorized using math that actually there was a planet out there. Now, we know that there's only ever been one man-made thing that has been out that far, and that was Voyager 2. And it took a bunch of pictures, and it's actually what discovered pretty much all of its known satellites. Before that, we didn't know it had a lot, we just knew that it probably did, but now we were able to count that it had 14. Now, one thing that's really cool about Neptune, besides the fact that it's blue from how much hydrogen and helium is in the atmosphere, it actually has its own weather patterns. So as Voyager 2 was flying by taking pictures, you could see storms in its atmosphere. Neptune also has rings like Saturn does. They're just very small. So Saturn's very big, very crazy, very unique, but it seems more and more the farther you get away from the sun, the more likely you are to have rings as well. Its core is made out of ice and rock, like Uranus. Now, here's the craziest fact about Neptune. Neptune, although it has more mass than Uranus, it's actually smaller.
It's smaller?
It's smaller.
It's smaller.
It's smaller.
And that has to do with gravity and density and how those all correlate to its atmosphere and size. And so we're going to try to explain that to you. Now, to do that, we're going to have to get rid of this board and just throw it over here. Thrown. throw it over here. We're going to move this on up. And we're going to go ahead and put this right here. So, go ahead and move that camera on in so that we can see this board right here. Mostly just the board. Mostly just the board. All right. So, we have Uranus right here and Neptune over here. Now, right now, they just have nothing. So we're going to have to add some mass material, which means we're going to need some rock material and atmosphere and gas. So I'm going to first add it to Uranus first. There we go. So we've got good old Uranus with some mass. Ooh, I rolled a 5, 6, 7. Oh, some other numbers, and I don't know what that is. But anyways, we have our mass over here with Uranus. 1, 2, 3, 4, 5, 6, 7, 8 pieces, let's say. So it has 8 pieces over here. All right, which means that over time, because gravities, what is gravity? Gravity is objects that are attracted to each other. So the law of gravity essentially says that these different pieces of rock are all attracted to one another. So that means they're all gonna get closer and closer and closer and closer together. Now, if they're mostly gas, they'll stay a certain distance apart, just like air molecules. They don't just disintegrate into nothing. So now we're gonna go ahead and add some Neptune mass. All right, now, as you can see over here, I have added a lot more Neptune mass because Neptune has a bigger mass over here, which means over time, these different mass particles are going to all scoot nice and close to each other, because of gravity, because gravity is attracting all of these pieces together over time. And that's what's going to be forming our planets in the first place. But the difference between Neptune, despite the fact that it has more mass, this also means it has more gravity. And because it has more gravity, it is strong enough to pull all of these materials close enough together that it's actually smaller than Uranus. Because it has more mass, so it has more gravity, so it ends up becoming more dense. And so, although if you were to weigh Neptune and Uranus, Neptune would be heavier, it is actually smaller. And so, that is the relation between mass, gravity, and density in our two different ice giants. Excellent then. Alrighty then. So, let's go ahead and bring you way back on over there where the sun is. And that is all the time we have for today. So, remember, your homework today is the same as last week, but this time you're going to be doing it with Uranus and Neptune. So design a probe that will explore one or the other. What are you going to do? Are you going to explore just the atmosphere, or are you going to design something boldly to go to the rocky core? Ooh, and maybe pick up some diamonds and bring them home and be rich. Excellent. Well, until then, goodbye now. Bye-bye. Bye-bye now. Bye-bye. Bye-bye now. Bye-bye.